My name is Klaus Holliger, and my work, or rather the work of my group, seeks to understand how we can use near-surface geophysics to address a variety of hydrogeological, environmental, and engineering problems.
Hello, my name is Andrew Geary, and welcome to Seismic Sound Off, in-depth conversations in applied geophysics. The shallow subsurface contains our drinking water and produces our food, and it is also where we ultimately discharge much of our waste. Recent history has taught us that overuse, let alone abuse of our environment, may lead to the long-term detriment to our livelihood. The protection and sustainable use of this fragile, surficial environment has therefore become a societal and political issue of critical importance. Near-surface geophysics has an essential role to play in this endeavor. Klaus, Holliger, and I explore near-surface geophysics using his SEG Honorary lecture as a starting point. We discuss the advantages of geostatistical techniques and two approaches to relating easy-to-measure geophysical data to more elusive rock and soil physical properties. This episode showcases the value of near-surface geophysics to the public and highlights cutting-edge techniques to better understand what's happening under our feet. Visit seg.org/podcast to register for Klaus's free lecture. And stay through the end to learn how in under 5 seconds you can show your appreciation for this free podcast. And now, my conversation with Klaus Holliger. And your honorary lecture, which is what we're speaking with you about, is called Using Near-Surface Geophysics to Estimate Soil and Rock Physical Properties. And kind of starting with something basic here, how do you explain near-surface geophysics to non-scientists?
Well, near-surface geophysics comprises a relatively wide number of techniques that allow us to look into the subsurface, pretty much like ultrasound, X-ray, or MRI scans used by medical doctors. The objectives are also largely the same. We want to see what is there, whether there are any problems, and if so, what can be done about them.
I feel like the audience could maybe start to piece together when you mentioned the ultrasound there. You know, what makes near-surface geophysics, though, on a geophysical level, particularly relevant for the general public that they may not be aware of?
The near surface is generally understood as ranging from the Earth's surface to the base of the first aquifer. In absolute terms, the thickness is therefore regionally quite variable, from a few meters to more than 100 meters. This thin surficial layer hosts a good part of our livelihood and is therefore also referred to as the critical zone. It is where we produce our food and our drinking water, but it is also where we place the foundations of our buildings, construct our subway systems, and ultimately deposit our waste. Continued demographic growth and associated industrialization and urbanization has rendered the Earth's near surface into a fragile resource that needs to be managed in a careful and sustainable manner. Near-surface geophysics can help us to achieve this objective.
What are a couple of near-surface techniques that are widely used?
Near-surface geophysicists use a large number of techniques, and everybody has his or her favorites. To answer this question, it is therefore interesting to see which techniques are used by non-specialists. Indeed, the democratization of our field has been one of the most remarkable and most positive developments during my career. Near-surface geophysics is now routinely used by many environmental and engineering firms. While this community has long been aware of the potential benefits, the widespread acceptance that we have seen during the last 2 decades or so was made possible by the fact that some of the instruments and data interpretation softwares became increasingly user-friendly. This is notably the case for electrical resistivity tomography, ground conductivity mapping, and ground-penetrating radar profiling. The ongoing evolution of seismic recording and interpretation techniques may lead to similar developments in this domain. Here I'm thinking in particular of seismic refraction tomography, as well as multi-channel analysis of surface waves. For the latter, I also see an increasing use of ambient noise, such as road noise, as being used for the seismic source.
You know, it's been common to use near-surface geophysical techniques to provide images and characterizations of the surficial environment, but your research group is focusing on expanding the use of these techniques. What is your research group working on?
I would not say that we are expanding actually the techniques, but we try to add value to them by relating corresponding geophysical parameters, which tend to be relatively easy to measure, to more elusive and more difficult to measure soil and rock physical properties. These properties are of direct interest to engineers and hydrogeologists. Prominent examples include the porosity and the permeability, which are required to manage and protect our groundwater resources, or the mechanical compliance of fractures, which can help to avoid undesired seismicity during hydraulic stimulation procedures.
Why are understanding rock and soil physical properties, such as permeability or fracture compliance, helpful in protecting our own livelihoods?
To protect and sustainably manage the surficial environment, we need to understand the key physical processes at play, such as, for example, fluid flow and contaminant transport. The parameters we measure in near-surface geophysics cannot be directly used for this purpose, but they can serve as proxies, which can then be related to the pertinent target properties.
What are the approaches you take to understand these rock and soil physical properties?
The beauty of soil and rock physical properties is that they speak for themselves, at least for specialists. For example, if we provide the porosity and permeability distribution to a hydrogeologist who needs to assess groundwater pollution problem, he or she will be quite happy, as this is exactly what is needed to run the corresponding flow and transport simulations. Conversely, our hydrogeologist would be scratching his or her head if we instead only provided the geophysical measurements. So what my group does is that we are sort of seeking to relate the geophysical measurements to the target properties that are used by the practitioners, and we do so in two different manners. One of them is through geostatistics, and the other one is through direct physical relationships, provided that the latter are sufficiently strong.
What is the advantage you gain by using your approach incorporating geostatistical techniques to better understand these physical properties under the earth?
Geostatistics allows us to make educated guesses of target property in places where we do not have any corresponding measurements. Quite importantly, it also enables us to quantify the corresponding uncertainty. Let us consider an example. In a water-saturated porous environment, the electrical current flow driven by a voltage gradient roughly takes the same path as groundwater flow driven by a hydraulic gradient. It is therefore reasonable to assume that there is a relationship between the electrical conductivity and the hydraulic conductivity. In practice, however, this relation is weak and site-dependent due to a variety of reasons, such as, for example, the competing effects of electrolytical and surface effects on the electrical conductivity. If we can establish such a site-dependent relation, for example, based on isolated borehole measurements of both the electrical and the hydraulic conductivity, then the combination of near-surface geophysics with geostatistics may allow us to regionalize this information.
You state in the description for this talk that the two approaches you offer are fundamentally different yet highly complementary. How are these approaches complementary?
We have seen that geostatistics lends itself to establish relations between geophysical parameters and rock physical target properties. Then the underlying causality is weak, variable, and site-dependent. For certain scenarios, however, this causality is remarkably strong. A key example is the relation between the dielectric permittivity, which we can infer from ground-penetrating radar velocity measurements, and the soil water content. This relationship is indeed so strong that an empirical relation, which today now is known as the top equation, and is based on a simple polynomial fit of a number of laboratory measurements from local samples, has turned out to be universally applicable throughout the world.
Who would you say is the ideal audience for this lecture?
One thing I've learned during my career is that I'm a terrible judge of my own work and its reception by the community. As such, I do not really dare to make a recommendation here. What I do, however, hope is that this talk will be an opportunity for our community to reconnect, also just virtually this time, and to rekindle professional and personal relationships.
Sometimes bringing this community together and this audience can really, it's great to get these scientific minds together. Are there challenges that you're facing in your research right now that you hope the audience might be able to provide some insights about for you?
Yeah, as scientists, we live we live a privileged life or a privileged existence, as we are able to work on what we personally consider to be interesting and worthwhile problems. As such, we risk to create our own little bubbles, which need to be pricked from time to time. In brief, in my view, the audience is always right, always knows best, and I'm thankful for any feedback.
What is a question you hope the attendees will ask themselves after listening to this talk?
Quite honestly, I neither expect nor hope that my presentation will lead to any kind of soul searching. My keenest hope, however, is that this virtual get-together will sort of stimulate discussions, spontaneous discussions of the kind that we used to have pre-COVID when we met in person, for example, at the annual SCG meetings.
Lastly here, what principle, teaching, or point of view has helped you succeed in your field?
I see my career as a cocktail of naive curiosity, lack of planning, and lucky coincidences. This could really have gone terribly wrong, and I do not recommend following this route to anybody. An important glimmering, however, which I had early on and which I internalized ever since, is the immense value of scientific collaborations. Teamwork is fun, and the compounded result is always better than the simple sum of the individual parts.
Well, that is a great place to leave it. We will link the information to sign up for this virtual honorary lecture in the show notes and on the website of SCG. And Klaus, thank you for making time out this evening to speak with me today about it.
Thank you very much, Andrew, for having me.
SCG produces Seismic Sound Off to benefit its members, the scientific community, and inform the public on the value of geophysics. To show your support for this show, please leave a 5-star review on Apple Podcasts and Spotify. Simply go to Seismic Sound Off on Apple Podcasts and Spotify on your phone. It takes less than 5 seconds to leave a 5-star rating and is the #1 action you can take to show your appreciation for this free resource. And follow the podcast while you are on the app to be notified when each new episode releases. Original music created by Zach Bridges. This episode was hosted, edited, and produced by me, Andrew Geary at 51 Features. The SCG podcast team is Jennifer Cobb, Kathy Gamble, and Allie McGinnis. Thank you for listening. This is Seismic Sound Off, signaling off.